Let's do some strength of material problem. This one is under curved beams. So yeah, let's read and try to see. Okay, obviously we have a force going down like that, and they're interested in this, what is going on there. But from our strength of material, wherever we learned that, we know that it's going to be force all over area. And force is what? Is P. What is P? 250 all over. What is area? It's this and that. Then let's just 75. Then okay, and then we get 3.33 MPa. I'm using MPa because this guy was an MMs. Let me shift the value at A. So this value is at A. So is this good enough? Obviously not. This is just a stress. If this thing was just straight like this and it was pulled with P. But now, because there's some sort of a curve, let me draw it like this. So just kind of explain what I'm trying to say. Now this force is here. That means there's some sort of moment that this thing is pulling by. Let me call it R. This moment that is causing here in the centroid. So it kind of looked like the problems that you did. They call them combined loading. So that's what it is. It is a combined loading type of problem, because now the moment is also induced by this arm. Okay, so we actually know a formula to calculate the stress for curved beams, of which is M open R minus R. I'll explain every variable as soon as I write them. RC minus R. So this R is neutral axis. This guy is neutral axis, the same as this guy. This guy is centroid. For curved beams, neutroid and neutral. I say neutral axis. If that's the neutral axis and center of mass are really not in the same place. That we have R and RC, and this guy is just some R or some position that we're interested in. If it was straight beam, it could have been Y, and M, you know what it is, and area, you know what it is. This guy is still the same as that guy. This is stress. So if you want to find max stress, you're going to check what is the stress here and the stress here. So let me say stress in and stress out. Let me just write them both, right? They're going to be whatever stress that I got there, which is 3.3 plus, okay, here I think by now you already see that this guy was tension, but yeah, it was tensioning, and I call positive, tension positive. It also looks like a T, and then plus M plus R minus R close all over A R RC minus R. So let's find each and every one of these values. Okay. So okay, let me put that aside. Hopefully we'll come back to it. Put just there. Okay. So we don't need that. Let's try to find R. R has a very good formula that there's a very good derivation for, and dA all over R, right? But you're looking at the square. There's actually a formula that actually you just plug in. You can actually integrate. It's also not that bad, but there's a formula that does that for you. It says B, I think says lean R big, or R, let me call it R outer, and I'll call this one R in. Cool. So that means that this formula is telling us it should have an area somehow. So area is going to equal, so we already calculated area, 3 by 25, of which is 75. This means here, we're going to have 75, right? And then 75 all over, what is B? B is this guy, 3 lean, the big R, or they call it R naught here. It's going to be Do you know any R? You know the inner one is 50, so big R is going to be 50 by 25, 75. Inner one is going to be 50, and then we can get an R. So if I compute, I'm getting 61.65. Let me should store that value at B. Okay, cool. It's R, so it's mm's. Units are important. Mm squared. Okay. So we already computed, and then let me call what was this guy? I think it was called R. We have it there. The only guy we need to find RC now, right? RC centroid is literally halfway, so halfway is going to be first R of which is 50 plus half of 25, 0.5 of 25, and then I'm getting 62.6. I mean 62.5. Let me store that answer at C, right? So let me make that one smaller and remove the math because I just want to call that guy RC. Right, we almost have everything we need here, do we? Okay, let's see. Let's bring back this. Oh, what have I done? Now we have that. Hey, why are you not getting big? Yes, we have. Okay, we have it here. Remember, I did outside and in because I just want to do one simple calculation. All these things are in MPAs. Whatever answer we get, it's going to be in MPA. So in or out is going to be 3.3 plus M. Oh, we need to find M. Okay. Whatever we're doing, M is force multiplied by arm, right? A force, I think, was given to be 250 multiplied by arm. Arm will be this thing is acting at the centroid, so it is our centroid, this guy, right? 62.5. so it's literally, this is a C, right, from here. So and then I'm getting 15625, and then that guy I'm storing at D, and that is my M. Let me go put it with the other friends of his somewhere there. Cool. Now we almost know everything, and I stored my M at D. Let me just put D there. R here is R of neutral axis. It was stored at B, minus R is R that you're interested in, of which you haven't decided which one you're interested in, all over area was just 75. RC is R centroid, it was stored at C, minus the same R stored at B. Then I'm going to do in, it's going to equal to, and going to do out. So what I'm doing, I'm just going to change for this one. Let me see, these are functions, right? R here, R is equal to, it's an in one, right? R is going to be equal to the in R is going to be 50. Here R is going to equal to the outside one, 50 is going to be 75. Why 50 here and then it's going to be 75? So I'm just inputting this R here, then whatever value that was stored in the calculator, then I'm going to punch just now. Also, this guy is also stored at A. I forgot that part, so I did it just here. So notice here, if I'm punching, I'm getting a wrong answer. Here I'm supposed to have 75, and then another R here. I think now I just punched exactly as it look here, and setting R is 50. Then I got 6.09. I mean 6.99299.899. So remember, these are also in MPAs. So this thing of storing values help you get the actual very correct answer. I know you could just try to put some, maybe the last 3 decimal places, but this guy is more accurate than that, obviously. So now I already have it in a calculator. I'm just going to set now X yes, R equals to 75. So this is just me calculating. Everything's exactly the same, but I'm setting you R to 75. If I do that, now I'm getting negative 40.661999933 still in MPa. So the question, I think they wanted the max one. I don't know, maximum stress. So maximum stress is going to be this guy because it's bigger. Remember, this guy doesn't mean it's small, it just means it's compression or tension. So this guy was positive and it was under tension, meaning this guy is is under tension. Is under tension. The guy is also positive because tension was positive in my case. If you think about it, let me see how can I actually try to convince you on that. We have a C beam that kind of look like this, and we cut it like that, and there's a force here, P. This thing is revolving around the center, whatever that. Let me try to take this guy, right? And if I'm pulling down as a P, you see that this thing will be kind of going like that. It'll be rotating like this. P is pulling it to go like that. If that's the case, that means the inner part should be under tension, while the outside part should be, you can see now this one is getting longer, this one is getting small, this one is getting compressed. Outer is negative, is getting compressed. Inner is positive, is under tension. Yeah, I think that's all. Thank you for watching.